All right, good afternoon, everybody. Welcome to Lecture 4. We had a bit of an issue with the live stream today, so we decided to call it off, and instead I'm going to record this separately for you. Okay, let's get right to it. In terms of announcements, there's not much to discuss today. I just want to bring your attention again to the timeline. This is something that I'm updating as the course proceeds. Make sure you have a look at the timeline every once in a while, especially if you miss a lecture or if you're a little bit lost of how the lectures proceeded in the previous weeks. I'm hoping to add pictures and videos to this timeline once I have a chance. I think there is the facility where you can add your own comments to this. And if you add comments either to this timeline or you add it to the bulletin board, which is also on the Moodle site, that might be a point of discussion for us in future lectures. Okay. The second thing is that, again, make sure that you check the HTML version of the notes. This will be the official version of the course lecture notes, and I'm moving, as the year progresses, I'm going to be moving stuff from the PDF files down to this HTML version. There will be the occasional new chapter. There's not going to be that many new chapters. You'll see that Chapter 4 here is now new. Chapter 4 is something that we're hoping to start in today's lecture. But the bulk of the course, essentially the middle contents of the course will be identical to the PDF. Okay, let's very briefly review what we covered last class. We discussed definitions of forwards orbits and orbits. This is definition 3.1. We also wrote down the exact criterion for a fixed point. A fixed point is a point in which x naught is equal to f of x naught, and what an n cycle is. One definition that we didn't cover in the lecture, or I might have only briefly mentioned it, was this notion of the invariant set. The invariant set is it's essentially a set here, so you see it's a set contained in R, which under the effect of the map always remains in the set. So x will be part of the invariant set, which we call S, if the orbit of x, if I keep on hitting x with my map, then all the later iterates remain in the set, and also all the previous iterates. So this notion of invariant set also includes the backwards orbit as well. Okay, so this symbol here are all the points that follow x forwards in time, and also that preceded x prior in time. Okay, this notion of the invariant set is going to come back, is going to be a really central topic in the future lectures that we have. The significance is not so clear now because we haven't really looked at examples where the invariant set is interesting. Okay, and then in the last lecture, we ended it with just a very basic informal definition of what stability is. And I explained to you that the issue with stability is that if I think of a point x and I think of point x as being stable, then by stable I might mean that if I start slightly close to it, so if this is x here and I start like close to x, if I start close to x, then eventually I get closer and closer to x as time proceeds. Okay, this is one notion of stability. But you can also think of the fact that if I have a fixed point x and I start close to this x, I don't ever get closer to x, but I might, say, oscillate around it. Okay? And so I remain near that point x, and I might still describe that point x as a stable point, even though the iterates don't get closer and closer to that point. Okay? And corresponding to those two ideas of stability are the two definitions of stability that we want to look at in today's class, which is one is Lyapunov stable, this is definition 3.4, and the other is quasi-asymptotically stable. If a system or a fixed point obeys both notions of stability, Lyapunov stable and quasi-asymptotically stable, then you describe it as effectively asymptotically stable. Okay? And so the basic idea is captured. Let's read the definition first, and then I'll draw the picture on the board. The basic idea, the definition reads, a point x is Lyapunov stable, which informally we say starts near, stays near, if for all epsilon greater than 0, there exists a delta greater than 0, such that if the distance between x and y is less than delta, then fn of x minus fn of y is less than epsilon for all n greater than or equal to 0. Okay? Don't worry about this next definition of the invariant set. I want to talk about the point definition of stability. This is the point definition of stability, and then this is the definition for a set here. The definition of a set will be very, very similar. You can read it on your own, but just on the board, let's draw what this definition means. Okay, so the definition stated that this point x, so I'm going to do the picture on the top here, I'm going to do Lyapunov stability. The basic idea is that you have a point x that you are claiming is Lyapunov stable, and in order for me to prove to you that it's Lyapunov stable, I tell you, give me a value of epsilon, and so you say epsilon is, say, 0.1, or 0.01, or 0.001, and so forth. And then I say that, well, I can guarantee to you that as long as I pick a point y, which is within delta of x, right? So I'll write down the definition on the right here. Okay, so if for all epsilon greater than 0, there exists a delta greater than 0 such that if the distance between x and y is less than delta, right, then the distance of the nth iterate of the map on x minus the nth iterate of the map on y is less than epsilon for all n. Okay? So in other words, your epsilon is a challenge. You've challenged me to basically make sure the orbit stays within epsilon. So this might be my epsilon here. Okay, so this distance here is epsilon, or if you want to be specific, you say it's epsilon over 2, because I just want to measure distance up and down. And so you've challenged me to keep the orbit within a distance epsilon of all the iterates of, so this here is fn of x. Okay, I've drawn it, by the way, I've drawn it so that fn of x is constant, but it doesn't have to be that way, right? This fn of x might also move around. I'll draw a picture of that in a second. And the point is that as long as I pick my y within a distance delta, then the iterates here will lie within that band, which is of size epsilon. Okay? Here I've drawn x so that it's a fixed point, but it doesn't have to be a fixed point of the system. Okay? We could have drawn the picture so that the iterates of the map x are also moving. So for instance, I could say that my orbit of x looks like, let's say this. This is fn of x as a function of n, and this system is Lyapunov stable if you start sufficiently close to this x, this y here, you'll remain sufficiently close. Arbitrarily close, so this is of size epsilon. If for all epsilon greater than 0, I can find a delta greater than 0 such that if the distance between x and y is less than delta, then the distance between all the images are always within epsilon. You're always in this tube of size epsilon for all n. Notice that this definition doesn't require that fn of x and fn of y, sorry, this graph here is fn of y. This definition doesn't require that the gap between these two numbers, or graphs, the gap between these two graphs tends to 0. You don't need it to tend to 0, okay? This is Lyapunov stable. All right, let's go to the next definition. Read the rest of this definition on your own, but the rest of the definition applies to sets instead of points, but the basic idea is the same. An invariant set S is Lyapunov stable if for any sufficiently small neighborhood U which contains S, there exists a neighborhood V which contains S, such that if x naught is an element of V, then the Ford's orbit of x naught is contained within U. Okay? Read that definition on your own and see if you can draw a picture of that on your own. If I remember, I'll do it again at the beginning of the next lecture or on Friday's course, or you can just ask me about it. But the idea between the pointwise version of Lyapunov stable and the set version of Lyapunov stable is effectively the same. Okay, let's go on now. The next stability The first one was starts near, stays near. If I start near the point x, I stay near the point x, or the fn of x, the images of x. Now the next definition, quasi-asymptotically stable, is, in plain English, it means tends towards, okay? So a point x is quasi-asymptotically stable, or tends eventually, or tends towards eventually, if there exists a delta greater than 0 such that if the distance between x and y is less than delta, then the images, the difference between the images, fn of x minus fn of y, tends to 0 as n tends to infinity. Again, the first part of the definition applies to points, and then the second part of the definition applies to sets, okay? But let's just understand the point-wise version of that, okay? So the point-wise version says that if there exists a delta greater than 0, so a point x is quasi-asymptotically stable, tends to eventually, if there exists a delta, so if there exists a delta greater than 0, such that if the distance between x and y is less than delta, right, then what you need, basically, you need the distance between the images to eventually tend to 0 for sufficiently large n. Then the difference between the images will tend to 0 as n tends to infinity. You can alternatively repose this as you have in some of your analysis courses to say that there exists a sufficiently large capital N greater than 0 such that this distance can always be made arbitrarily small for little n greater than that capital N. But this, for us, this definition is sufficient. If there exists a delta greater than 0 such that if the distance between x and y is less than delta, then the difference between the images, the distance between the images, tends to 0 as n tends to infinity. Then x is quasi-asymptotically stable, QAS. Here, I'll finish this definition, and x is Lyapunov stable. Okay, so in terms of our picture, again, I don't want to be misleading and make x into a fixed point here, because the definition doesn't just mean for a fixed point x. We're going to take this to be our x, and again, we're going to say this is our images, fn of x. Then you would describe this point x as quasi-asymptotically stable if there exists a delta such that if you were to take a point within delta of x, by the way, I've drawn this always, I call this delta rather than delta over 2, but you can call it delta over 2 if you like. There exists a delta such that if I pick a y which is in delta of x, then eventually, for n sufficiently large, the distance between the two tends to 0. So this here is fn of y. Notice that according to this definition, there's not a requirement that the image of y stays close to the image of x. It's allowed to stray further away, which is different from Lyapunov stable. In Lyapunov stability, you always have to, if you start near, you have to stay near. In quasi-asymptotically stable, you don't have to stay near for all time, but you eventually have to tend towards. Okay? If you have a point x here, which is both Lyapunov stable and quasi-asymptotically stable, then you would say that it's asymptotically stable. So this is the strongest kind of stability for our purposes. Right? So asymptotically stable means that as long as I start near that, if I can start sufficiently near that point x, I'm always going to tend towards it for large enough n, and I always remain close to it for all n. Okay? All right. So that covers this next part of the definition. In addition, it's interesting that actually neither of the above definitions implies the other. I can find systems which are quasi-asymptotically stable but not Lyapunov stable, and I can find systems which are Lyapunov stable but not quasi-asymptotically stable. Okay? It can be proven that for a one-dimensional map f with a fixed point x naught, if the gradient of the function is less than 1, if the magnitude of the gradient of the function is less than 1, then you have asymptotic stability, and you have both Lyapunov stable and quasi-asymptotically stable. If it's not less than 1, then it's neither. Okay, and as we said before when we talked about this condition on the absolute value, if the absolute value is equal to 1, then yeah, you don't know enough. This is just a typo. Right, okay. So the next thing I want to do is I want to start covering Chapter 4. And Chapter 4, as it's written at the very top of this description, is actually a new addition to the course. Previously, when we started what you'll see as Chapter 5, we needed some techniques that students might not have encountered previously, techniques involving series expansions of functions. So this year I wanted to put in this Chapter 4 just to make sure that you know the basic ideas of using series expansion methods. Okay? Now, why are you learning some of these things? The reason why is that you'll remember that when we discussed the cobweb diagrams and when we discussed stability, you'll remember that when we discussed stability of the logistic diagram, we eventually came to the conclusion that if you want to study stability near a fixed point, so remember a fixed point is where the line y is equal to x intersects with the curve f of x, a point that always remains there. What we were interested in characterizing was if you move slightly further away from that point, then is it stable, is it Lyapunov stable, asymptotically stable? And the condition that we found, which we just stated, was that you have to look at the gradient of the function, f prime of x, okay? The other realization we had when we studied this situation was that you're not necessarily concerned with the behavior of the function everywhere. You're only interested in the behavior of the function near that special point, near that fixed point, right? We have to work with the idea of expanding the behavior of functions near special points, and then to use those series expansions in order to study, in order to probe at the behavior of the functions. And so the basic idea is that we're going to take our functions, f of x, general functions, f of x and mu with a parameter mu, and to study those functions near their fixed points, okay? And the tool that we're going to be doing, the tool that we're going to be using to do this is essentially Taylor's series expansions. We're going to take that function f of x and mu and start expanding it about special points in the system. Okay, so this Chapter 4 is a review of some concepts that you might have learned in other courses about series expansions and about the notation that we'll be using for the next, for Chapter 5 and onwards. Okay, so let's go back here. Okay, so I'm going to review for you essentially three things or four things. The first thing I'm going to review is a Taylor series in 1D. Then I'm going to review Taylor series in 2D. And then I'm going to introduce to you special notation that you use to essentially compare series. So things like ordered notation, much less than, much greater than, and asymptotic. You might have encountered some of these symbols informally in other courses, but we're going to introduce it to you systematically. And then finally, I'm going to introduce to you probably a new tool that you haven't seen before, which we can call the method of dominant balance. And we're essentially going to be using this method of dominant balance, in order to solve equations that we wouldn't necessarily be able to solve in closed form. Okay? So the basic review that we're going to start off with is Taylor series in 1D. Okay, and the point is that you're given a function f of x, and you can expand f of x near a point x using the Taylor series formula. So you approximate it with the value at the point x naught itself, And the correction term involves the gradient with a linear shift, x minus x naught, and then you add the second derivative over 2 factorial, and then this x minus x naught squared, plus so forth and so on. Okay, the basic idea is that you're given a function. Let's say here's my function. I want to make my function slightly more complicated than just a parabola. And you've expressed the function in terms of a series expansion about this point x naught. And that allows you to approximate, for example, values at arbitrary x. The closer x is to x naught, the better these series approximations if you only use a few terms. So the very first approximation is that you're going to approximate the value of the function here, f of x naught is at this height, with its value at x naught, which you can see is not very good except if x is really, really close to x naught. The next kind of approximation you'll use is a linear approximation. So this is f of x naught plus f prime of x naught. You collect the gradient at that location, and then you multiply it by the line x minus x naught. So this is the line that goes through that point, and so you're going to use this height instead to approximate the value of x naught. If that's not good enough for you, you can then add a quadratic term, and now you're going to add a little parabola that approximates the function, and that parabola is then obtained by the 3 terms, and so forth and so on. Then you can correct it with a cubic, and then a quartic, and a quintic, and so forth and so on. That's the basic idea of Taylor series approximations. Okay, so just as examples, right, sine x about the origin is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial plus so on and so forth. As x tends to 0, so this approximation gets better and better as x gets smaller and smaller. Okay. You don't have to know a lot of these formulas. I don't think we're ever going to be working with Taylor series for more general functions, but there are 2 functions. Well, there's really only one function that you should really know for this course. If I expand 1 plus x to the alpha near x equal to 0, right, let's just try it. We'll try the formula. For chapter 5, you're almost never really going to be using that formula. You just expand things manually. But let's just try it. So let's take this example. This is sort of a binomial expansion. Then f of 0 is just 1. Then f prime of 0 is just alpha. Sure, I'll write it out. You take a derivative, then you substitute in the point. This is just alpha. And then so forth and so on. F double prime of 0 is just alpha times alpha minus 1. Okay? And so from this, you'd conclude that f of x is equal to 1 plus alpha times x plus alpha times alpha minus 1 over 2 factorial times x squared plus so forth and so on. Usually you don't have to, we're not going to need to work with too many terms from that. Okay, but this is something that's worth knowing because you're going to be expanding some of these things with 1 plus x to some power. So, for instance, 1 plus x to the 4 is 1 plus 4 times x plus 6 times x squared plus 4 times x cubed plus x to the 4. Okay? Because the derivatives will eventually be equal to 0, this series will terminate. So, and this is just the binomial expansion that you might have learned. And in A levels, 1, 4, 6, 4, 1 are the coefficients of the Pascal triangle. Okay, good. So this is just a very quick review of Taylor series in 1D. You should know this formula here, 1 plus x to the alpha, just because you're going to be using it over and over. The other useful version of this formula is if alpha is equal to minus 1, this is the geometric series. And I'll do another example of that now. just to show you again the type of manipulations that you should be familiar with. And if you can't remember this, that's okay. Just flip open, a calculus book and just review it. So here's another example. If I wanted to get the expansion of tan x near x equal to 0, this is sine x over cosine x. Okay. One way is for you to set f of x equal to tan x, and then you take derivatives and substitute in x equal to 0. But that can be a bit of a pain. It's not too bad. You just have to think carefully about how you differentiate a tan function. The other way to do it is just a trick here. You write the series expansion of sine x on the top. This is x minus x cubed over 3 factorial plus dot dot dot. And then you write the series expansion of cosine on the bottom. That's 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial. I don't need this many terms. And then you write this bottom here as 1 minus r. Okay, so r here is x squared over 2 factorial minus x to the 4 over 4 factorial plus dot dot dot. And then you essentially use the formula that that 1 over 1 minus r is 1 plus r squared plus so forth, the geometric formula. So this gives you x minus x cubed over 3. And then in brackets, it's 1 plus r squared. 1 plus, let's write r, x squared over 2, plus dot dot dot. I'm not going to need it. And then r squared plus dot 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 plus dot dot dot. This is actually a minus. It's minus x to the 4 over 4 factorial. Okay, then you can expand this out, and you just have to cluster the powers. So just count up in powers of x. So the first one is x. The next largest power has to be x cubed, because I can either make an x cubed taking this x and this x squared, or I can make an x cubed taking this one and this one here, this x cubed and this 1 here. So the next one will be an x cubed. I can either have a minus 1 over 3 factorial, or I can have a 1/2. And the next one will be an x to the 5, and so forth and so on. Okay. I'm just showing you one way of doing it without having to take the derivative f prime of x and f double prime of x. Just this basic manipulation using this trick of moving a series from the bottom up. This trick you kind of use often essentially to move a series, an infinite series, which is on the denominator, up to the numerator. If you haven't seen this trick before, then once you see it, it does become a staple in your toolbox. Okay? All right. So this was just a very basic review of Taylor series and series expansions about points. Usually the points that we're working with are just series expansions about the origin, but not necessarily the case. All right. This covers this initial bit about Taylor series, just some basic examples that we've done. This is another basic example which uses the trick of moving a series from the bottom to the top. Okay. The last thing to end up with is just this Taylor series in 2D. So note, so this is definition or theorem 4.2. I think giving this the name of a theorem makes it sound a little bit more important than it actually is. I don't actually know how often we're going to use this formula. So I'm just kind of warning you that. So note, Taylor's theorem in 2D for f of x, y around the point, let's call it P. It's the basic idea, which is the same as the 1D case. You want to write down an infinite series for this f of x, y about this point P. And so it's a combination of its value at that P plus all the values of the derivatives at that point. okay, around P is, so f of xy is f of x naught, y naught, plus f prime. I'm going to write that as subscript, and I'm going to stop writing f naught, x naught, y naught. I'm just going to write this as P, meaning you evaluate x at P. You evaluate this gradient at P, and then it's x minus x naught, plus fy at P, y minus y naught, plus, and then now you need the mixed derivatives. You're going to have an f xx at P times x minus x naught squared over 2 factorial, plus it's 2 times fxy, x minus x naught, y minus y naught, evaluated at P over 2 factorial, plus the symmetric component. Okay, and before you start writing this and being a bit worried, I've never seen this before, that's okay. I think there might be 1 or 2 homework problems related to this, but it's not a major component of this course, right? Again, this is just setting up this idea of of infinite series expansions. Most of the manipulations that we're doing from the course, we're not going to be working with these formulae. We're just going to be manipulating quadratics and cubics and expanding them and simplifying them in different ways. You'll see that the definition given here is exactly the same. The difference is that I've written delta x and delta y instead of x minus x naught and instead of y minus y naught, respectively. Okay? This expansion of this operator here, delta x dx plus delta y dy squared, once you can expand it out and you'll just verify it, it gives you exactly this. Okay, let's move on. So the next thing I want to cover is notation. And the basic idea of this notation is that we want to develop a notation that allows us to compare the behavior of functions as 2 functions approach a limit. Okay? So it's very, very similar to when you first learned about L'Hopital's rule, that you might not have learned the reason. So when you were in school and you learned how do I evaluate this limit of sine x over x, the basic idea is that sine x tends to 0 and x tends to 0. And so you get 0 over 0 and the teacher tells you, well, it's indeterminate, so you can't really make any conclusion of 0 over 0. The key is that both of them are tending to 0, but they're tending to 0 at a certain rate that they're tending to 0. And it's that rate that you're trying to investigate. So you end up taking a derivative of the function. L'Hopital's rule, you take the derivative on the top over the derivative of the bottom, which is just the basic idea of comparing rates. By taking the derivative, you're able to basically, when I was a school student, I thought of it like an onion. You're basically peeling off the layers of the onion and looking at some deeper behavior in the system. And in this case, the easier way to do it is you just write down the series expansion, right? And then you get to cancel the leading order term, and that's just 1. Plus dot dot dot. These dot dot dots is an x squared, which tends to 0 as x tends to 0. So this is just 1. L'Hopital's rule is just the trick of doing that by taking derivatives. But the basic idea is that in order to investigate this behavior, you basically peel away the layers by expanding the sine function into its series approximation, right? And that's the basic idea that's going to inspire the notation that we're about to present. How do you compare different functions as they approach a given limit? Okay, so I just realized that everything that I wrote is quite difficult to see because I didn't have the camera active. Okay, so in this next bit here, you can follow the notes. It says essentially we want to define precisely what we mean when we say that 2 functions, say f and g, exhibit the same behavior in some limit, say epsilon tending to 0 or x tending to x naught or x tending to infinity. So for a given limit, you want to somehow express that f is behaving like g, or that it's much larger than g, or that it's much smaller than g in that limit. And that's going to inspire this definition 4.1 of these different notations. The example that I gave involving L'Hopital's rule is very similar to the inspiration behind this notation. You want to state that the behavior of x is similar to the behavior of sine x as x tends to 0. So this inspires you to introduce this tilde notation, this squiggly notation, tilde notation, okay? Right, so the definition is as follows. You're going to introduce a much less than symbol which you use two less than signs, and that is also going to be equivalent to a much greater than symbol and read in the opposite way. And then you're also going to introduce this notion of similarity, or sometimes is asymptotic too, this similar similar terminology. Okay, so this is now definition 4.1. And we're going to introduce that symbol there, much less than, that symbol there, much greater than, and that symbol there, tilde, or similar to, or asymptotic to. So this guy is much less than. This guy is much greater than. And this guy is similar to, or asymptotic to, okay, just right. Much less than, much greater than, and then just right. Okay, so the definition is as follows. We write f of x, let's just write f, as much less than g as x tends to x naught if the limit as x tends to x naught of f over g is equal to 0. Okay, that's what it means to be much less. In this case, we say that f is much less than g as x tends to x naught, right? As an example, for example, sine x is much less than cosine of x as x tends to 0. Right? I know that because the limit as x tends to 0 of sine x over cos x is equal to 0. Okay? The similar definition for g is much greater than f of f. So I can define it as g is much greater than f if the limit as x tends to x naught of g over f is equal to infinity plus or minus infinity. Or you can just define it as g is much greater than f if f is much less than g. And then you have the above definition. Okay, so the same thing applies here. You'd say that the cosine function of x is much greater than the sine function of x as x tends to 0. And then finally, if the behavior is just right, similar to or asymptotically to, right, we write f tilde g as x tends to x naught if the limit as x tends to x naught of f of x over g of x is equal to 1. Okay, so for example, sine x tilde x as x tends to 0. It's important for you to specify the limit in which you're making this claim. If you don't write the limit, then it's ambiguous. Sometimes, if the book is sloppy or if I'm sloppy, I won't specify the limit because it's assumed that you know what the limit is. But you're always, these notations, much less than, much greater than, and similar to, you're always, or asymptotic to, is asymptotic to, that's the other way of defining this tilde sign. You're always stating this in the context of a limit. Okay? Now you can think of other examples. Let's write down some other random examples just off the top of our heads. You can take the limit as x tends to infinity. So what are some other examples? So for instance, I can have x cubed plus sine x plus e to the minus x. I can state that this is tilde x cubed plus x plus x squared as x tends to infinity. Okay? Why? Because, I mean, intuitively, why? Sine x is a bounded function. It's always between 0, -1 and 1. This is exponential decay. This always tends to 0. So the dominant behavior of the left-hand side, the biggest behavior is x cubed, and similar, the biggest behavior on the right-hand side is also x cubed, and those two behaviors are equal, and therefore that's why you write this similar to. If you want to use the official definition, then indeed the limit as x tends to infinity of x cubed plus sine x plus e to the minus x over is equal to 1. Okay? If you were to plot, the other way of seeing this is if I were to plot the top function and I were to plot the bottom function, they would both be exploding as x goes to positive infinity, and they're both exploding like a cubic, like x cubed, even though the top function has kind of this funny behavior where it might be oscillating, especially close to 0. Because close to 0, this term here is contributing less. Okay? So this is actually a very intuitive notion of comparing functions in some limit, comparing the behavior of functions in some limit. Right? Let's look at another example. So for example, you might have tan x tilde x plus x times e to the x as x tends to 0. Okay? So again, you can either plot the function, in which case you'd see what's happening, or you just prove it. So here the limit as x tends to 0 of tan x over x plus x squared e to the x is equal to 1. How do I know that? Well, I know that tan x behaves like x is tilde x at leading order. So the first term of this Taylor series approximation, we just stated it's like sine x, and that's like x. I also know that as x tends to 0, that this guy here, x squared, is tending to 0, like an x squared, and e to the x is tending to 1. And x squared is much smaller than x, as x tends to 0. So I know that the dominant term on the bottom here is like x. If you want, I can do this. This is the limit as x tends to 0 of x plus dot dot dot. That's the first term of the Taylor series for tan x. And this is just x plus dot dot dot, and that's equal to 1. Okay? The other way that you can see it is that you could have just plotted the tan x function, so that here's a tan x function, looks like that. And if you were to plot this function here, x plus x squared e to the x, you know that it behaves like x to begin with. I'm not even plotting x properly. You know that it behaves like x to begin with, but then it explodes like x squared e to the x, but you don't care about what happens out there. You only care about near the origin. So if you were to plot the top function with the bottom function, and you zoom in really close to that origin, you'd see that they look very, very similar. So again, this is the inspiration of that symbol, that similar to or asymptotic to symbol. Okay, finally, so we've covered, let's go back here. You see, I'm doing a much better job associating the notes with the lecture. So some examples that we've looked at: sine x tilde x. Sine x is similar to x, which is similar to tan x as x tends to 0. X squared plus x plus 1 is similar to this function as x tends to infinity. Again, just look at the function on the right-hand side. The top tends to infinity like x cubed. The bottom tends to infinity like an x. So in total, the top over the bottom tends to infinity like an x squared, and you have x squared tilde x squared. You've extracted out the dominant behavior, the most important behavior as x goes to infinity for this right factor. And then similarly, sine x is much less than cos x as x tends to 0, because sine x indeed tends to 0, whereas cos x tends to 1. Okay, now in the last bit of notation that we have to introduce is this notion of a big O notation. Let's read it together. In the examination of limiting processes, often the main issue of consideration is the relative sizes of quantities defined according to their powers. For example, if x is a very small number, with x being 10 to the minus 5, then x to the 5 is much smaller than x in terms of our notation. So x to the 5 is much less than x. X to the 5 is much less than x, as x tends to 0. On the other hand, we might not care so much about the difference between x to the 5 and, say, 5x to the 5. We place them on equal footing because they have the same power of x. Their growth rate, or their decay rate, is comparable to one another. And so you'd like to set up a relationship between x to the 5 and 5x to the 5, but you can't say that x to the 5 twiddles or tilde 5x to the 5 because their ratio doesn't tend to 1 as x tends to 0. So that introduces this notion of the big O notation. Now, I can just tell you definitively you're never really going to need to use this big O notation because there's a much looser version of it that we're going to be using. But I'll read out to you the definition nevertheless. Definition 4.2 big O. We write that f is equal to O of g, big O of g, as x tends to x naught, to mean that there exist constants k greater than 0 and x star greater than 0 such that the magnitude of f is bounded as less than k times the magnitude of g for all x minus x naught less than x star. Okay? As I stated, we're not going to be working with that definition of big O. There's a much more intuitive notion of big O that we'll work with. Okay? And I'll write it out here. So in this course, we will say that f is equal to order g in some limit as x tends to x naught if f tilde is k times g for some k, for some constant k, and that constant cannot be equal to 0. Okay, so for instance, 2x is on the order of sine x. Okay, because you're comparing essentially leading order powers. In this case, the leading order power, this thing here, is tilde x minus x cubed over 3 factorial. And this definition is insensitive to the leading number in there. You're just comparing the leading power. Okay? I should say that all of the examples that we use in this course are algebraic. So the power is always say x to the 5 or x to the 15 or x times y. These are all algebraic powers. We're never really going to work with very complicated things like logarithms or exponentials or sinusoidals unless they're easily discounted. Okay, so these definition of order notation and much less than and much greater than, if you read them up in a book or in a separate treatment of asymptotics or in a separate treatment, you'll see that they have to be posed in a much more general way because often the behavior of the functions is much more complicated. We're just looking at simple algebraic behavior. Okay, let's leave it at that. It's been a pretty long lecture. I'm sorry the stream didn't work out as well as it should have this time around, and I'll see you next time.